Hey everyone, moving to the next chapter here, which is direct current. So what we're looking at is trying to attach batteries and wires to different things in a circuit. And just like this woman, you want to make sure you know what you are connecting to. The thing we want to talk about now is the movement or the flow of charge. And something you can ask yourselves, how do we know when something is flowing? How do we know that there is what we call maybe a current? What we talked about in class is what is happening in wires. We charge up capacitors and discharge capacitors. We connected those capacitors to light bulbs and we watched them discharge. And we want to know, how do we know if things are actually flowing? What causes charges to actually move in the wire? To talk about what is happening in wires, let's look at some of the highlights from that lab. So you can see here what we're doing is we're taking a battery pack and attaching that battery pack to the capacitor. The positive terminal is touching the positive terminal of the battery and capacitor, and the negative is touching the negative as well. So once we disconnect the capacitor here, there are 4 locations we want to focus on. We want to focus on location A, B, C, and D. C and D being the bare wires at the end. B being the positive terminal, and A being the negative terminal. Once we look at those 4 locations, we want to put a voltmeter across them. And as I touch each of the locations, A to B, you can see I get about 4.3 volts. We're then going to touch B to C, and you can see basically 0 volts. Touching C to D, you get negative 4.3 volts. And then D to A, we get 0 voltage again. So there's no potential really in the wires, which means there's no field. Go ahead and sketch the charge distributions there. A and B are the plates inside the capacitor, and C and D are the wires. What I'm going to do now is connect C and D together and watch the voltage change. When I connect A and B together, the voltage drops off very quickly. And if there's a voltage present, that means there's an electric field present across the capacitor. We knew that. But one thing that may be new to us is what happens in the actual wires. So I'm going to do this one more time, connecting B and C, and you can see there's another dip, which is something you may not expect. That means there's a potential difference in the wires. If there's a potential difference in the wires, there must be an electric field that's pushing charges through the wires. What we're now going to do is, instead of sending them just through the wires, we're going to send them through a light bulb. You can see the capacitor is charged around 4.4 volts. And when I touch the wires there, you can see there's a drop off in energy in the light bulb now. Instead of just a dip in the wires, we're seeing a curve that takes a little bit longer than we had the first time. What I'm going to do the second trial here is get a longer bulb, so a different filament. And we're going to push those charges through the longer filament, and you can see it takes a little bit longer for it to discharge. So comparing the 2 graphs up there on the top, you can see that different filaments bottleneck the charges differently. And we see when we lose our potential difference, our electric fields get weaker and weaker until there's no potential to push charges from high to low. When we switch out to the second lab, we have step 6 here where we're just using battery packs, wires, and light bulbs. And in this setup, what we're doing is having 3 batteries attached to 1 light bulb, and what we're going to do is measure the voltages at different locations. So you can see in the picture up there, we're measuring from A to B, and we're getting about 4.1 volts. When we then switch to measure the voltage from B to C, we're going to see that if there's a potential or an electric field in the wire, and there is, at negative 0.01 volts. When we go across the light bulb though, we see a drop in voltage of negative 4.09. And we're going to do one last measurement from D back to A, and we see a negative 0.02 volt loss. So as you go around that setup, you want to add up all the volts from the battery and then subtract all your voltages through the wires and the light bulb. In step 7, we're going to change up the setup just a little bit here, where we have 2 light bulbs attached to our 1 battery pack instead of 1. You can see the picture up above. We're going to go through the battery packs, through the wire to bulb 1, another wire to bulb 2, and then from that bulb all the way back to the battery pack. We're going to measure our potentials and our electric fields along each of those locations to see how the charges, field pushes, and where the pushes are the greatest. You can see the work done is 4.18 joules to increase the voltage in the charges. We then lose volts in the first wire. We lose about 1.95 volts in the first light bulb. another 0.1 in the wire, we lose 2.17 in the second bulb, and we lose another 0.1 back to the battery. There's one last setup here, which is step 8. And in step 8, you're going to see a diagram here where we're going to have each light bulb have their own path back to the battery pack. So rather than sharing one path, we're going to have multiple paths, and you can see how the light bulbs change up a little bit. There's your picture. You can see there are 6 different locations that you want to focus on, and we're going to again measure the battery pack at 3.9 volts. We will measure just a few locations here for you. You can see this voltage in the wires, but across one light bulb it's 379, and across the second light bulb it's 375. So there's voltage in the wires, but there's also voltage across each of those setups. So go ahead and complete the rest of your lab packet based on the information you watched there, and let's talk about what we're seeing in what is happening in wires. So what we got out of what is happening in wires lab is this idea that potential differences are created when there's an electric field, and electric fields push charges from high to low volts. Does the positive charge move from the capacitor of the battery through the light bulbs, or is it some negative charge moving from the negative plate up to the positive plate? And that debate was brought up for many, many years. People didn't know whether during a discharge positive charges moved or negative charges moved. It was a big question. So one way to solve this was the Tolman-Stewart experiment. Accelerated a piece of metal that would have free charge carriers, and depending on the charges that were able to be moved, think of inertia, as the plate accelerates to the right, things that are mobile would want to stay at rest and pile up on the back end of the bar. And what they saw was that the electrons were loosely held to the atoms. So the electrons must be the charge carriers, and those were the things that got left behind when the bar starts to accelerate. So what this means is that there's an electron current. So when we have electrostatic equilibrium, charges are moving rapidly all over the place and there's no net movement. But when there's an electric field present, which we saw comes from a voltage, the entire sea of electrons moves in the direction, kind of like gas going through pipes or water moving through pipes. When there's a potential difference, charges want to flow from high to low. We still bow to convention and we say that positive charges flow from the positive terminal of the battery all the way through the circuit to the negative terminal of the battery. All that this means is that truly electrons go from the negative terminal of the battery and move all the way to the positive end of the battery. The light bulbs or whatever you're discharging through does not care which way the electricity actually is moving. It just cares that there is movement of charges and that energy is lost. So again, the charge pumps, the batteries, create a potential difference. In order for water to flow, we have to have a potential difference from high to low. And if I wanted to look at the number of water molecules that pass through at any given moment in time, I'd have to look at little n times V times A. Little n would be the amount of molecules per unit volume. Area would be the size of the pipe. That would matter. And V is the speed, how fast water molecules moving through the pipe. And if you look at that, if you take little n being number per unit volume, you take velocity, meters per second, you can get rid of one of the meters, and you multiply by an area, that's meters squared, that's going to knock out the rest of my distance units. And what you'll get is the number of water molecules that pass by every second. So if we apply the same concept to charges and wires, to maintain the flow of charges, there must be a difference in electric potential, which means if there's an electric potential created by the battery or a capacitor, there must be an electric field. So when we get charges to finally move, we call this electric current. So just like water flows in a pipe and we say there might be a flow or a current running through there or through a river, we have electric flow, which we call the current. It's the amount of charges that pass through a given point at any moment in time. So the definition of current is dq dt is the change in charge per second, how many charges pass through a certain area. And so since we want to label that as coulombs per second for the amount of charge flowing by, Ampere is the person that studied this flow of charge, current, the name amps. The variable we use for current is I. Unfortunately, we've run out of letters again, So I know is a moment of inertia in your mechanics, but in electricity, I is going to measure the amount of current flow. The charge is passing by every single second. So let's try an example problem here. We've got 1.56 times 10 to the 20th electrons passing through a point on a wire in 5 seconds. So what would that current look like? Current is the amount of charge that passes through every single second. All I was given there is the amount of the electrons. I know a number of electrons. But to know how much charge went by, we know a way to do that. We take the number of electrons and we multiply by the electron charge. Doing that should give us the amount of coulombs that pass by every single second. And if you do your math there, you should get around about 5 coulombs per second, or we call that 5 amps. So that's how you can solve for the amount of charge passing by any single moment at any single time. It's not the exact number of electrons, but it's the amount of charge that passes by. And one note down there says that the current passing through each part of the wire is the same. Looking at the next, current per unit area, or current density. The current density, unfortunately, is called J. J is the amount of current passing through a particular area. So if I wanted to find the current density for a 0.1 diameter wire, let's solve for the J. I know that there's 5 amps of current. When we're looking at a wire here, all we need is the area of this front part here. And the area of that is just pi r squared. So give us the diameter of the wire here. To get my current density, I'm going to take 5 amps over pi r squared. Make sure that your r is in meters. So 5 amps over my area gives me a very large current density, about 6.4 times 10 to the 6th amps per meter. Wire changes sizes, like you can see in this picture, goes from a large area to a smaller area. The amount of current will stay the same, but the current density, how thickly packed that current is going to increase. So what does current depend on? Well, one thing we could say then, that if this is our wire, we'll have amount of current flowing through it, so many charges flying through per second, and we know that there's an area associated with how wide the wire is, and there's a length of the wire here. So if I wanted to know the amount of charge carriers I have per unit volume, what I could look at is maybe the total charge in a segment of wire. So the total charge here would be my charge of 1 electron. My little n here would be the charge per unit volume. So how many charge carriers do I have in a given volume? And multiplying that by the volume of our wire will tell me how much charge I have. Remember, that volume can be written as area times length. So the size of the wire multiplied by the length of the wire will tell you the actual volume of charges you're looking for in that setup. And if I want to solve for the current, I can take that as charge per second. So since I know charge would be based on the charge density times Q times area times length all over time, what I can see here is that I do have a length divided by a second. And length divided by a second we know as speed. So one last way of writing this would be NQAV, where V would be the drift velocity of the charges as they drift through the wires. So this is how you'll see it written on the AP sheet. It'll be the number of electrons per unit volume, or the charge of 1 electron, multiplied by the area of the wire, also multiplied by the drift speed. And if I wanted the current density, remember that current density is current per area. So if I take everything I have here for current and divide that by area, what knocks out is just the area. So the current density ends up being NQ times the drift speed. Getting those things will tell you how much current you have per unit area, and doing the I equation down there tells you how many amps are flowing through your circuit. Exploring what is happening in wires. Voltages create electric fields. Electric fields push charges and force them to go from high to low potential. And as charges start to move, we now define that as current, or the flow of charge.